Hello everyone, my name is Sheng, and this is a work I have done during my summer research at Vector Institute as a research intern. And today I'm honored to have Professor Nicolai to facilitate this presentation. Okay. So before anything, I'd like to go straight and talk about the contribution of this paper. And the main contribution is that we proposed this architecture, DOM QNet, which is a type of graph-based deep Q network, and we wanna frame the web navigation with this architecture, and we wanna solve it. So we have done some evaluation on the benchmark results, also with ablation studies, and also some multitask learning. And compared to the previous work, this is actually the first work that tried to solve multiple instances of web navigation tasks at once with one architecture, with one model. So some of the characteristics of the model. So first of all, it's very modular in a sense that you can explain this architecture at a very high level. And there are much less feature engineering so that it's very easy to prove to a new problem setting in a similar environment. And lastly, with this architecture, we were able to solve most of the this benchmark tasks at this and achieve a state-of-the-art performance for most of the tasks without any human demonstration or some sort of prior knowledge. And so now we want to go to the motivation of our work. Why did we do this work? And there are basically two perspectives here. Firstly, if we think about the web accessibility nowadays, some people might not be really familiar with the web interface. And this work, basically, with this work, our goal is to basically have a prompt where you can type natural language and solve the task for you. And at better, higher level, we also want to see if we could actually get some knowledge, extract some knowledge through the web navigation instead of accessing the knowledge base in how the question answering is done today is basically you use some sort of knowledge base, but in the future we want to explore whether this could be extended to question answering. So from the algorithmic perspective, there are basically two points that we found. Firstly, there's not much research in reinforcement learning community that your state representation has both the structured, which is sort of HTML or physical body of the robot. That's the structure part, and also you have unstructured data, which is the natural language. So at the same time, web navigation, we have actually a much larger discrete action space than the games that we see today, like Atari or other gaming environment. So that's another thing we want to investigate with this work. So before, I guess, getting into the technical part, I'd like to mention how this task is different from the previous task used in most RL literature. And at the center of this presentation, you could see for Atari, we've taken the pixel image, and then we output what action you want to take, i.e., what joint movement and button you want to click. And for robot locomotion, your state input is basically the position of each of your joint for your robot. And your action is basically you want to say how much we want to move for this joint and so forth. But for our task, we basically want to take in the HTML structured input, and then we want to output two types of action, click or type. And so I like to show a simple demo of our result. I mean, the task solved with our architecture, and basically see how we were solving this. So basically, you have you'll have a natural description at the top, which is part of the input. Another input is your web page, and these are the input and the output. As you can see, from this like blue like part where what it's actually doing. And for example, you click search and now it goes to page 3 and then it finds the matching result. So yeah, so we will have another demo later, but so this shows you like the basic idea of the task. Okay, so yeah, I'll go over with like basic RL and the graph neural networks first. And for RL, basically the goal of reinforcement learning is that you want to train an agent that interacts with this environment, and then we want to frame this process as a Markov decision process, which is a tuple of 5 elements here. And basically, in Markov decision process, you have a state. Your agent needs to produce the action based on that state. So your goal is to learn the policy pi a condition on the state. And while you're learning this, how do you learn this, right? You have an environment where there's a transition probability t here, meaning that based on the action that your agent takes, what next state it transitions to, and it's basically it's the probability of transition to that next state given your current state and then the action you take. And another part of the environment is this reward function where it's a function of state and action, and your agent takes a state. I mean, your agent is in a state, and it takes an action, and the reward function says, okay, based on this state, how much reward can you get with that action? So you can see it's basically this interaction, and the agent can learn the optimal policy pi to try to maximize this return, which is the total discounted future rewards. So for understanding how we can learn this optimal policy, we'd like to go over some key terms. And firstly, this Q value, state action value. So what it says is basically the expected. So we talked about we talked about the return. So this is basically the expected return when you're at state S and then you decide to take action A. So it's a value that estimates how good this action is, and it also considers like all the future rewards after you take this action. So, but the thing with this Q value is that it's based on your policy. So with different policy, you will have different Q, even though you might take the same action at the same state. And the goal of RL, is to basically try to maximize this, this return by saying, okay, given all those Q values with those different policies, what is the best policy? And then you can learn that you can get that by following this optimal Q value function, which says like, under the same state and you take action, and then with different policy, you'll have different Q values. But here, if you can, the optimal policy is basically that if you follow the highest Q value at each state with this action, then then that's the optimal Q value function. And the property with optimal Q function is that it satisfies this Bellman optimality equation. And this is exactly how we can learn, how we can understand like how to get this optimal Q value function. Because if you get the optimal Q value function, then you solve the MDP because you just need to follow the optimal Q function. So now we go to how we combine deep learning with reinforcement learning. And the idea is like we just said we need to learn this optimal Q function, and then we can approximate it. We try to train a neural network that approximates this. And let's say we can have this optimal Q function. Then your policy is simply the greedy action with respect to this Q value. Then it's a deterministic policy, but you can basically follow this policy and then get the highest reward. But how do we actually learn this Q star? If you don't have a Q star, then you can't really do this. And as we mentioned earlier in the Bellman optimality equation, it's a sort of consistency equation where you have this Q value you want to approximate, and then you can have a target value, which is this part in the right hand side of the optimality equation. And then by minimizing this, you can learn the optimal Q function, and then you can use the policy. So now we'll cover some graph neural networks, which is basically the representation of which is basically to represent a graph. So how do we represent the graph in like vector space? There are basically two phases in graph neural networks, and there's a discrete framework called neural message passing neural network, and it covers. There are a lot of variations of graph neural networks, but this framework sort of organized them and put them into a very high-level framework. So how do we represent the graph? And for graph, you have vertices, which is V, and you have edges, which is E. And for graph, you can either represent each of the node individually, or you can represent the entire graph as a one vector. So the message passing phase basically tries to represent each node of your graph. And the way you do that is that let's say you have an initial initial representation of each of your node. So how do we have this? You can just use a word embedding or something to embed it. So that is basically its H. H basically means the initial. H basically means the individual feature representation. And the point of message passing is that even though we embedded this each node, you haven't really incorporated the neighborhood for each of your nodes. So the point is you want to do some sort of this aggregation from your neighbor into each of your nodes. So this shows how sometimes it's called graph convolution because you have a center node, and then you have adjacent. Let's say your center node is this HV, and your adjacent features are H omega. So omega is basically the neighbors of your center node, and then you can do this aggregation by this function M, and then as an example of function M, you can simply have like this weight matrix. You multiply the weight matrix to each of your neighbor node representation, and you basically just sum them up. So that's the very basic way to do the message update. And this E is basically, it's the edge feature. So like for different edge, you can have different weights. But here, for simplicity, we ignore that. We assume all the edges are same type. Yes. Sorry, it's a quick question.
So that EV, will that construct your weight matrix? Is that so that EVW, will it construct your weight matrix, or it's a separate thing?
So EVW basically is like, let's say you have different type of edges. Then we can use this EVW as sort of index. Like in word embedding, we index into different embeddings, and this can become an index. So yeah, for different E values, then you have different W.
Gotcha.
Okay. So it will help us make it like a directed graph versus
right. So for this framework, they actually assume like undirected graph. But for directed graph, you simply just change the adjacency matrix. So you can solve it's just a slight different frame, but it's the same thing, basically. Yeah. So that's the message update. So you aggregate the information of your adjacent features. And then now you want to do an update to your center, the node that you actually care about. And the way you do it, it's sort of like this kind of recurrent. This kind of reminds us with the recurrent neural network in a sense that you have previous hidden state and you have a new update. So this HVT is basically previous state, previous node state. And this M is the aggregated representation you just computed, and use another function to update it. So I just mentioned recurrent neural network. So obviously there was a work that used gated recurrent unit to do this update. So then you update your node that you actually care about. And we repeat this process for 3 times because now if you think about this process, it's only updating your adjacent feature to your center node. But let's say you care about something that's far in the graph, then you have to apply this multiple times such that the features there can be incorporated in your center node. Okay, yeah, so finally, yeah, sorry.
So you have these 2 layers of aggregating the data. One of them is with convolution. The other one was this gated recurrent unit. Right.
Yeah. Actually, I think that's maybe a good way to think about it in the sense that here you are doing sort of graph convolution. You're using the shared weight to multiply to each of your neighbor, and here you're doing this recurrent update for your center node with taking your previous hidden state.
So you take the neighbors and you do the convolution. For the node itself, you apply another function, which is doing this gated recurrent.
Yeah.
I see.
So finally,
and how does it help? Instead of having just like a convolution, normal convolution.
Right. So the point of this is like it's a flexibility. So like obviously you can just add them. You can add the neighbor representation and just add it to your center node. But this is just another flexibility, and then in that case, in your case, U is basically addition as a function.
Sorry, we have a question online. On slide 6, can you explain again what the H omega do?
Slide 6 or 7, you mean?
Sorry, 7.
Okay. H omega here. Right, so HV is like you have a graph, and then let's look at one particular node. Then the representation of that node is HV. And then let's look at the adjacent nodes of that node, which is omega. So H omega is basically that representation. So they're both like embedded in the same way. It's just when you look at the center node, H omega represents the adjacent representation. And in practice, those are ones that show like 1 in your adjacent matrix. So like, right. So exactly. Okay. Yeah. So finally, we might want to.
Sorry. I hate to interrupt you, but very quick question before. One, I didn't listen too well on that side. So on your GRU, you have your H's, which are, I believe, the hidden states of your GRU, and then you have your M sub VT plus 1. What was your M? Was that the
Right. So M is basically your adjacent, aggregate representation of your neighbor nodes.
Why is it T plus 1, if I may ask?
Oh, okay. So like, say we're at T equals 0, we have the initial embeddings, nothing happened, and then at T plus 1 equals 1, then the next update, like the the question is why this is T and this is T plus 1.
Yeah, I was
so like for example in Rn you can think of this is like HT minus 1, and then here it's like a new input, right?
Yeah. Okay. So here essentially you do convolution and also then you do the recurrent input. It's 2 steps. In the convolution you also have the node itself as well in the function. So you do the convolution and you also apply it to the node itself, and then you do the recurrent, this gated recurrent unit by having reconsidering the adjacent nodes. Is that the idea?
Right. So this part is sort of flexible, and based on what you just said, I can understand. Like, let's say like in some paper they do attention. So like here, I'm only multiplying the weight for the neighbor adjacent matrix, but I'm not actually doing anything with the center node in this step. But for example, if you want to do a graph attention, then you can use your center node as an attention query, and then your solutive neighbor as like values, and then you do attention, then you actually use the center node somehow. But this is just sort of for flexibility that in this message update, you can either use the center node or you don't need to use it.
The M function would define how is it incorporated in the convolution.
Right. Okay. So finally, we want to represent the entire graph as like one vector. How do we do that? So we basically consider another aggregation function where this time you aggregate all the node feature vectors in the entire graph. And it shows very simple. Like this basically means that you take so in the message update you perform it t times. So we take the last time step features and then we apply this R function. And R function, for example, very simple, which I also actually use, is max pooling. You basically max pool each of the feature, like each dimension of your features for all the nodes, and then you can get like one vector for your entire graph. Or you could do some summation, or you could also actually some works use like neural network that for each node you pass into some sort of a neural networks and do a summation, or you do summation and pass into a neural network. But yeah, R is also very flexible here. Okay, so that's the.
So sorry, what was Y again? The embedding?
The Y, right? The Y is the embedding of this entire graph.
Right.
Yeah.
So it's like a single. It's right. Vector for the whole graph.
Right. It's a single vector for the whole graph. Right.
Sorry, quick question.
Yeah.
So T is the number of, I guess, adjacent nodes in your graph?
That depends. So this T is sort of like hyperparameter. Let's say you want to actually aggregate information in the entire graph, then you have to pick T, which is the largest sort of, the longest distance between two nodes. But yeah, it's a hyperparameter depending on your problem. Right. Yeah, if you don't have enough T, then some information at very far nodes cannot be like incorporated here.
So T is number of hops essentially, right?
Right, yeah, number of hops. Yeah. So I'm going to talk about like our work in the RL and on a web interface, but there was some like actually previous work there. And the first work was this MiniWoB. The work proposed this MiniWoB benchmark environment, which is actually very good because web navigation, it's very hard to define a task, and they proposed this standard set of tasks. And I think 1 year ago there was also this another work by people at Stanford. They also proposed the architecture DOMNet, and then they proposed some type of workflow guided exploration, which basically kind of, because the web navigation is a sparse word problem, you have a very, and then at each time step you have very this large number of actions. So this exploration basically sort of used the XBAR demonstration to constrain your action space such that you can solve the task. And then finally, there's actually a parallel work recently which used a few like tricks like curriculum learning, reward shaping, and also shallow encoding, which they actually able to solve this book flight ticket task, which is very hard in web navigation task. And it's also another good work to look at. And finally, for our work like with graph neural network and reinforcement learning, previously there is also a work at University of Toronto Vector Institute. They basically model the physical body of a robot, because if you think about a robot, people usually just feed in each vector of each representation of your joint state, which is basically the position, like the position of each joint, but they don't really use the relational information. For example, my arm is connected to my upper body somehow. So they actually model that with graph neural network, and then with that they obviously can transfer better to other learning tasks in locomotion. So now I'd like to formulate our task as this web navigation as Markov decision process, because that's how you could apply reinforcement learning to solve this task. And for MDP, as mentioned, there are 5 tuples, and in particular here, the state, as you can see from this illustration, is that you have your natural language description, which is instruction, and then you have your web page, which we will parse the HTML a tree structure, and then those two are the combination of two is our state representation. And the action you take is that we frame it like in 3 action categories. So for this task, for example, in the first step, you actually have to type this this name into the search box. So here you actually use this. One more thing is that we also have to define the mode, because when we do web navigation tasks, it's very explicit that we either type something or we click something. So this is like another sort of augmented action that we consider. And for this task, for example, at the first step, we need to type. So we would like to have the A mode as type. And then for typing, you actually have to care about where you type and what you type. So for where you type, you look at the DOM tree, and then you pick one. So that's the action. The action is, remember that the action is dynamic. The graph size changes, so the picking the node of your graph is basically the action for the DOM. And then you also have to pick the token that you want to type into. So that's basically, we look at this natural language, and then we pick one token from this sentence. So that's after that, the agent can perform this step to type the Kinesia into the search box. And then for the next step, we actually want to click the search. So then you set the mode to be click, and then you choose this search DOM. So the DOM that has the tags for the text for search. And then as you can see, then similarly you can move around the pages, and then you find this person, and then if you complete this if you get, so they programmed it such that if under this situation, if you click like Kinesia, then you get a reward of 1. So that's how this problem can be framed as a Markov decision process, and then we can solve it with RL.
So the Markov decision, my understanding was that it's based on the assumption that the actions are independent, right? But in here, so actions are dependent. So that's what you're trying to capture. Is that correct?
Right. So for this to be a Markovian, we just need to make sure that our state captures enough information here, for example, such that I can forget about whatever I did or whatever state I was in previously. So here, basically, just looking at this page, and then I can know, like, it says 9, so I just need to go to the 3rd page. I don't need to know I just typed Kinesia because it's already typed in there. So this previous action, whatever you did, is already captured in this state representation. So it's Markovian. It satisfies the Markovian property there.
So imagine that it decides to type, right? So when it decides to type, then clicking is not an option, right? So, but can you clarify a little bit, sorry?
So the agent has to pick one action for each of those. So you have 3 action categories, and then you have to pick one action for each action category. And then, yes, you either click or type. You can choose.
Right. So, for example, if you're doing the typing, so you have to choose from the, characters, right? So the subtask that you have is dependent on the task you have, right? So, for example, you want to type Kinesia, and the agent has understood that, okay, I have to type. So the next action would be what I should type, right? So it's like it's dependent on the previous one. Or how do you define the actions exactly?
This is actually, I think this will show in the next couple of slides, because what you're getting at is the 3 things that you see. For example, in the first one, DOM search box, Kinesia type. This is an action, right? So it's not like you're choosing the type and then you're choosing you choose one at the same time.
It's a whole package of action of type.
Right. Yeah. And then they're chosen independently, but Sheng's gonna talk about that.
Right. Yeah. Yeah. So yeah. Oh, wait. Sorry. Okay. Yeah. So firstly, I like to mention.
So we have a couple of questions. Alec, do you want to go first?
I just have a quick question on your previous slide. So the set G that you have there, is that a finite set, or is that something that's parsed? Do you have to actually parse natural text to get the words like you want to enter it, for example, Kinesia?
Right. So the G is basically the each token in the instruction.
Could you please repeat the question? Also, you might want to sit in the front.
Okay. Right. So he asked me about like if this G is like, do I need to parse anything for the G? And I guess suppose my answer is like you have a sentence and then you parse the sentence to individual tokens, but you still keep the like the sequence of the token. That's the answer? Okay. Yeah. So is there any?
Alec also, did you have a question?
Just clarifying again. Just when the action is you're at a box and it's time to type something, does that action then get passed off to something else which handles the typing, or is it integrated into the entire?
Right. I guess that seems to be a very similar question to yours, and so actually I'm going to talk about it later. But let's say there are two ways to think about this kind of problem. Let's say we want to log into Facebook in a login page. We can, obviously what we type depends on what we click, right? So like, let's say if we want to type our username, then we have to make sure that we click on the username box and then type it. So yeah, there is a conditional dependency there if you think it that way. But another way to think about how agent can act is that, let's say you go to a login page, you don't care what you're going to type. You always remember that I always look at the password box first. So that's the DOM part, so DOM select part. And I always type the password first. So here, like in this sense, you don't actually need to know that, okay, I have to type the password because I'm looking at the password. If I go to a Facebook login page, the first thing I do is I look at the password box and I type my password. You don't need to have a dependency there.
And what was DOM again? Sorry.
So yeah, so the DOM is basically you choose which part of your graph you want to do the action, and for this action you can either just type, you can just click that one, or you can type for that. And if you select type, then the second token is consumed. Otherwise, it's not consumed.
I think another way of looking at DOM is HTML elements. So you take the HTML code of a page, and then you have head. This would be one DOM element, right? And then underneath head, you would have, for example, these other elements, and each of them would be a DOM.
Oh, I see.
It stands for Document Object Model.
Right. Yeah. Yeah.
An abstract.
Yeah. I actually forgot to mention about that. But DOM is basically like, it's basically an object, and then like object has different attributes. So like each widget is a DOM, but each DOM has attributes like text or type or something. Yeah. So okay, I guess I'll move on. And then so I just mentioned like we have like 3 action categories, and if the naive way to sort of implement a Q network that handles this kind of action space is because you're thinking as like a tuple, so you have to actually consider permutation of the actions. So for typing, for clicking this DOM, I mean for choosing this DOM, what are the tokens that I can put? What are the mode I can put? I can have a permutation in that sense, but then this argmax part basically means that for the A, for each A DOM, I have to iterate over all the A mode, and then I have to iterate over all the A token, which is very computationally expensive, because then A DOM has the action space of V, which is your graph, and then A token has the action space of G, which is the number of tokens in your instruction. So it becomes quadratic. And then for this one, for example, there are actually 250 actions based on this way of framing the action space. For Atari, this wasn't really a problem. They actually consider permutation or pushing the button and moving the joystick, and it only gets 4 to 18 actions. But we have to do something for the web navigation. Yes.
Sorry, so I may have missed this, but like, so What is the actual goal of the agent in the context of the web page? Like, what is the agent actually trying to accomplish?
Right. So for example, for logging, basically, if you are able to successfully type the username in there, type the password in there, and you are able to submit the form, then you get a reward of 1. And how do we define this? The task, someone wrote a program to define this for those environments that we're investigating. Yeah. So another way to actually reduce the computational complexity is actually what I just mentioned about how we want to factorize our function, our action into 3 separate. This can be done if we assume, that all those actions are independent. We actually don't need to assume it to be independent, because you just need to have sort of conditional dependency within your queue network. But for simplicity, here we're assuming they're all independent actions. And in my previous example for the Facebook login, the task can still be solved with this assumption. So then you can simply decompose this Q value into 3 separate Q value, but but the goal is your behavior policy is still dependent on this Q star without the decomposition. But with this assumption, you can do the argmax for each of them. In that sense, you only need to have OV plus G, because here you only have a computational complexity of V, and here you only have a G, and they're separate. So this is how we should design the network such that it reduces the computation.
Could you kindly just repeat that quickly? So how did you reduce the space?
Right. So we in the last page, remember, we need to do this argmax here. We always need to do this argmax. But imagine if this Q can be decomposed into these 3, then the argmax operation can be factored out for each of them. In that sense, then when you do argmax, then you don't need to consider permutation. You can simply consider what to click without worrying about what to type. Yeah. So another thing to consider is
what is token mode?
Token mode.
Yeah.
Right. So a token is what token you select from the instruction to type into your
characters that you choose, or
the word token. So,
I see.
Yeah.
Okay. And how about the mode?
The mode is basically you either type or click. It's more for the environment. Yeah. So finally, we want to address the dynamic action space, because our graph changes at every step because the page changes. So how do we do that? So remember that neural network is a universal function approximator. So we can have 2 types. We usually have 2 types of Q network. And the first one is you're only taking the state, but you output the Q value for all your actions. So the problem here is that you have to define your architecture such that you know how many actions you're going to have a priori. But within our context, this isn't feasible, because we actually don't know how many DOMs we have in each page. So, but this obviously is computationally more appealing, because you can do a single for pass and then get all the Q values. Another way is basically you consider the function where the neural network as taking the state and the action. In that sense, this is also sort of we share the weights for different actions, because your network also taking this action, so you're actually not dependent on number of actions you have. And the promising thing about this type of architecture is that now you can sort of generalize. Let's say some actions you may never take this action, but because those actions are similar within the representation, so you can still generalize those Q values for those actions that you haven't even taken. But the problem is here, you might have same number of the fully connected layers in between, but here you only get 1 Q value, and you have to do this for all the actions. So it's more computations involved. So finally, I'd like to go into our architecture, and a high level basically it has as I mentioned, we have 3 Q values. So I have 3 Q streams, and then I have 3 representational modules for your HTML, which is local, neighbor, and global. And so this part is basically the network that actually we actually use. And this part is more like the problem formulation, where you have a web page, and then you have like the tokens. You have you consider tokens. You also consider this page as a tree of DOMs. And so we'll go deeper into each component here. Firstly, like the local module. Local module basically is the basic way of, because HTML it's a graph with symbolic representation with each node having like different attributes, and we have to actually we will use like word embedding to actually embed each symbols. So this part is basically that, and so for this diagram, for example, we can embed tag, class, text, like those attributes. For each attribute, we have an embedding, and so that's the left part. So that's this part. And then also we found that if we do some sort of similarity score with your instruction, it actually converges much faster, because you sort of feeding this whether your token actually matches with something in your instruction. So that's the right hand side. But the catch is that we only do this if this attribute is present in both your HTML and then also in your instruction. For example, text attribute. And then we will do like this, as I mentioned in the graph neural network, we will do message passing, because if we look at this diagram, we can see like some tag, like the checkbox representations are exactly the same in local module, because their objects are exactly the same. But in reality, like humans know that this checkbox corresponds to with this text. And how do we do that? We can do the message passing in the graph neural network. And this is basically it's a different ways of writing in the background for the graph neural network. But for example, here I'm using the basic multiplication of the weight as a m function, and then I use GRU as the u function for the vertex update. And so yeah, we perform this for t times, and then we get this neighbor module, which is basically the message passing for the graph neural network. Yeah.
This one was very clear. This one was very clear. The previous one I didn't get actually. What was going on over there? Could you?
Right. So here, for like let's say for this checkbox, we do a word embedding for the text. We do a word embedding for tag. We do a word embedding for class. We do each, and then for those ones, for example, focus. Basically, if it's focus and temper, whether it's being clicked, those ones can be incorporated as like a one-hop vector, 1 or 0, and we basically concatenate all those embeddings as one vector, and that's the representation for that DOM with our message passing.
Gotcha. And what did you do again with the cosine similarity?
Right. So if for that part, basically, for example, for the text, like if there's like SR here and this is the SR there, we want to give a similarity score of this DOM with your instruction. So like with SR and then SR, then it has a very high, but if high similarity score, but for some other DOM, it has very low similarity score. And this is sort of a scoring between the similarity between the token and the DOM.
I think my question is then how do we, so if I understand correctly, right, you want to bias your training such that embeddings of those similar items are closer in hyperspace to each other.
Right.
I think that's the idea. Well, the question is then how are you achieving that? So is it part of your cost function? Like how do you? I think that's what I don't understand.
I see.
Chef, while you're thinking, may I just say something?
Yeah.
The point, the way I understood that, the point here was to expand a little bit away from literal matching. So if you have a tag with text that's SR1, for example, you would still have the way you embed it, of course, depending on the way you embed it, you will still have a pretty high cosine similarity. So it's not just to do literal matching. You're not looking for exact text or whatever in these attributes, but you also include some kind of similarity that allows you to go beyond just literal matching. So you could have something similar, but not exactly like that.
Right. Okay. I think your question was more like, how do we make sure that when we train, the embeddings that should be similar are like closer in hyperplane? And the high level idea is with RL and then those embeddings, if you can't have that sort of representation, then you can't solve the problem. So like we train the agent end to end, and then if we actually train the agent to behave optimally, then it will naturally learn the representation such that they make sure the ones that should be similar are similar, like closer in hyperplane.
I see. So I guess then, I guess I'm trying to understand E attribute, E goal.
Right.
Those are the items that you want to be similar to each other, and you're getting EI local. Then is the entire sort of what is EI local? I guess.
EI local. All right. So EI local basically is the representation of one vector of your DOM. Mm-hmm. And the way we get it is that we basically embed all the attributes and concatenate them. And this second term is simply just sort of like additional step we take such that let's say we want to say like for this DOM, for example, is there a similar word in your instruction? And if there is, then this value cosine distance with this value and that particular value here is 1. And then we do a max, and then for others, it's small. So it gets a very high value. But let's say the word here doesn't appear at all in your instruction, then you'll have like 0.1, 0.2 or something. So even if you do a max, it's still very small.
Gotcha.
Right.
So if the understanding is correct, that you have this goal over there, which is like tokens, then from the HTML part, you try to capture the relation between these two by embedding the graph structure of, the web page to a like embedding, and then try to compare these two embeddings, and then try to maximize the similarity between these two embeddings, right? Right.
So yeah, this max part is just saying like, is there a word? Is there a similar? Is the text in this DOM?
In the goal and the DOM are similar or not? Is that
right. Yeah.
And then the whole idea of this embedding is that you have the representation of the state, so you can feed it in the RL algorithm.
Right. Yeah. We basically need, this is like initial step in like all the NLP stuff. You have to do a word embedding for each token, and then you pass it to a neural network.
But it's just representative of the states, not the actions, or it's also this kind of graph networks are representative of the action as well.
Right. For this task, it's very vague that, okay, this part of representation is state and this part of representation is action. It's sort of a mix because this representing this also means representing action, because clicking here is actually taking in the representation of this DOM.
In the DOM, it's already embedded the actions.
Right, yeah, it sort of have this action as an action. Sorry.
Maybe I've had one, but I'm not quite sure. So my question had been, why we're we searching over the goals? And the goals in this case are, if, for example, you said SR could be one of the goals that we were searching over. That would be the SR that we had parsed. Oh, okay, actually, I noticed that it's actually written there. No, that's fine, thanks.
Okay. Yeah, I could go over this more in like the break for this part, but I'll move to the next slide. So I mentioned this one, and then, yeah, finally, for the readout of your graph neural network, you have to represent the entire graph as one vector. And the way we do it, we tried it just using max pooling. And then we max pool for the local and neighbor representation, and then we get the representation of this entire graph as one vector. And the point of this module is that, let's say all the checkboxes are clicked, then you want to have a representation of that kind of state. It's kind of a proxy to that sort of state with this global module. So if all the checkboxes are clicked, then this module provides a very unique state that your Q network can take in.
So how you're sure that it's getting the max would give you a unique, representation? For example, you have two images and then.
Right. So yeah, that goes to like all the question in deep learning, like how do you do that? And if we do train everything end to end, then optimization will make sure to do that if it's a good, I guess, sort of.
So the maximum idea is that you have an aggregation over the E local and E neighborhood, right?
Yeah. So the idea of max pool is that like if the agent might learn that if something is not clicked, then that feature is very high. So if you do max pool, then you might get something very high feature values. But if you train it end to end, then if everything is clicked, then you make sure all the values are very small. And then even if you do a max pool, do you get like so like?
About this high and low, I was like.
So, like with optimization,
right.
It'll make sure that the max pool will give you unique. I mean, it might not make sure, but with the task, if you getting better sample efficiency, then that means this module is definitely doing something. Right. Or not this module, but I'm actually showing like evaluation studies for each module.
It empirically improved the model.
Right.
Okay.
Yeah.
Can you go back to slide 16 for a question?
Yeah.
How large would T be? So can you repeat that? It's not T.
So T.
Yeah. How large?
Right. So in our case here, like we tried 3 and 7 because we found like 3 is actually a good value because generally like the information, like for example here, you only need to aggregate the information of text here into the checkbox. So you only actually need 2 propagation steps for this one, but we use 3. And then for some hard task, you might have to use, let's say some context is very far, then you have to use a very high value. But yeah, we tried 3 and 7, and they're sort of like, yeah, the values that we're using. Yeah, so yeah.
So the max pooling is between those two E's?
Max pooling is basically max pool over like, so for E local, you have E local for each embedding, and you do a max pool for them.
So
for the graph, you do max pool
for
graph.
each I, right?
Right.
Okay. Yeah, gotcha.
Yeah, so we also try the attention, like for the readout. For the readout, I mentioned previously we do the max pooling. Another thing is you can do the attention where, for example, for this DOM, for this entire graph, your attention query is your goal. So how much each DOM is relevant to the query, and then that's the thing in the bracket, and that gives us the attention, attention between 0 and 1, and then we aggregate by, we aggregate all the information. So it's just attention, but we're using the goal as a query to attend to the each DOM representation. Yeah. So finally, how do we train this?
Yeah, I'm just wondering if the number of hops are so small, then how do you think of a GRU in the first place?
I think the previous works, I think 3 it's not a very small value in graph neural network. Like I think it's a decent, like if you do too much, then you might get a lot of noise, and GRU is just an option, it's a good candidate to try on. So yeah.
And sorry, can you again say what was the goal of this attention, applying this attention?
Right. So the attention is to see, for max pool, we just max pool without any conditioning. Right. Here we want to condition on the goal sentence. Based on this instruction, we want to have a different representation for
So you have 2 architectures. One is max pool, the other one is attention?
Right. We actually just concatenate them and try them together. Yeah. So how do we train this? Network? And because you have 3 Q values, and the thing is, you can't really do you have to do a TD learning for the sum of the Q values, because the sum of the Q values is actually the Q value that represents how good this action is. So when we act, our policy could do the argmax for each of the, with respect to each Q value, but when you train, you have to sum them up as a Q value and then do the TD learning. Right, so this is some like hyperparameters that we used, and it shows like some questions that were asked. For example, we performed 3, and then like we found like the social media task had very like much bigger DOM, so we actually have to use 7. So we actually also could just use 7 for all, but it's just more computation there. And some vocabulary size just show like this task is still like a toy task, in a sense. We don't need that big vocabulary size, and for each embedding, it's very small here, like 1632, etc. And yeah, so yeah, other ones also you could just look at.
I guess 7 for social media task. Do you have any like literature in mind?
Sorry?
Do you have any literature in mind for this 7 for social media task?
So
I mean, like a reference and a paper, because.
No, the thing is for 7 was like I look at the HTML. Right. And then I see that there you actually need like 7 steps. You have like 7 edges between those 2 DOMs that actually need to be incorporated. Yeah. So I guess we can go sure.
Let's thank the speaker. Technical mirror.
So those two. Action space is something that is by construction something you just like decide a priori.
So yeah,
how can it be like situationally agnostic?
Join our Slack channel to discuss it with others. Create a 5-minute video on it. Submit the video by April 15th. Win a cash prize. 5 minutes is short, so your challenge is to focus on the most important part of the paper, the most important concept, and help your audience. You should avoid trying to jam too much content. 3 important tips. Pick an 5-minute paper challenge. To win one of our cash prizes, Hello everybody! Welcome to the ACE 5-minute paper challenge. To win one of our cash prizes, you're challenged to make a video that communicates the interesting parts of your favorite recent machine learning paper. The video will be judged based on their technical merit, quality, and how engaging they are. Here are the steps. Select your favorite machine learning paper. Let us know what paper you picked. Join our Slack channel to discuss it with others. Create a 5-minute video on it. Submit the video by April 15th. Win a cash prize. 5 minutes is short, so your challenge is to focus on the most important part of the paper, the most important concept, and help your audience imagine and understand just that. You should avoid trying to jam too much content. 3 important tips. Pick an interesting paper, obviously, and learn about its context. Use a well-lit room and a good microphone for the recording. Try to be concise and do not cover more than one major concept. If you want to participate and are uncertain about how to make your video, drop us a line. We will try our best to help. We'll look forward to seeing what you make.
What do
Okay.
We asked Sheng to start.
Okay. Yeah. So for our experiments, so like our paper is about this network, DQN network for graph. So for our experiments, we have to pick our reinforcement learning algorithm, and we basically picked the vanilla DQN and then added some methods from the rainbow DQN. For example, we use double DQN because the Q-learning overestimates the Q value, so we use double DQN. And because Q-learning is off-policy learning, where you use experience replay to keep sampling your transitions that you experienced, and you want to have some prioritization based on the error, like the TD error that we get. So and also for Q-learning, like the problem with one-step Q-learning is that it has a very high bias in the sense that you don't know your target, like you're only estimating your target Q value. So there's some sort of bias, and then we want to get some lower bias, and by trading off some variance by sort of like mix of Monte Carlo and then TD learning. So you do multiple step of the rollout, and then you do the TD error for this multiple step. And then finally, we found like we were using epsilon greedy, but it seems like for our task and for exploration, the noisy network within the parameter space actually helped. So we also tried the noisy network. So those three methods, you could read them for more details. Yeah. So we use our architecture to solve like 22 out of 23 tasks, which are kind of very like representative tasks within this benchmark environment, and then we were able to solve it without any like expert demonstration or some prior knowledge, using using the least amount of like feature engineering to solve like 22 out of 23 tasks. And we were unable to solve this email inbox task, and the main reason is that for this task, the task has a very sparse reward. And for other tasks, they also have sparse reward, but we were able to solve it because the task has different instance of like smaller subset of tasks, which are, some of them are easier. By solving those easier tasks, the agent was actually able to generalize over the similar task, but has a longer horizon. And that's why we were able to solve 22 sparse reward tasks. But for this task, it seems like we do either need a very good exploration or expert demonstration. But another thing we found, like we were able to actually solve this Tuesday task, which has a very actually high long time horizon, but we solved that because this task actually has very similar sort of actions that you need to take, but if your network can generalize over like this sort of state and action representation, then it was able to solve. So regarding the question asked earlier about like why we need like each of the local, neighbor, and global module, and then we did like ablation study for two particular tasks to investigate this. Firstly, the biggest, I guess it seems to be obvious, but the biggest thing is like that we do need this message passing in graph neural network, which is why we choose graph neural network, because if you don't have a graph neural network and do the message passing, like all the nodes some of the nodes have exactly same representation, even though they have different contexts. So for click checkbox, without message passing, you actually don't know where you're clicking, like with the text description of your click checkbox. So it wasn't able to solve it without this neighbor. So I'm not sure if you can see this right now, but basically it shows like minus means we take that module out. And if we take out the neighbor module in the brown curve, then we weren't able to solve it. And for other local global module, we also investigate them and have seen that only like this blue curve, which has all the three modules, successfully solve those tasks with much less samples, and even for better performance for this task, for example. So I guess the last experiment we did was like, so this was the first task, sort of first work to do multitask learning for those tasks, because to do multitask learning, your network architecture has to be very general for different tasks. Otherwise, you have to switch your network architecture for slightly different web navigation tasks, which is why the previous works, they sort of had different number of like embedding size, etc. for different tasks, and they didn't actually try to do it for multitask learning, but we tried to do it with our network architecture. And this algorithm is sort of lengthy, but it's actually a very simple idea in a sense that for each task, you have an agent acting on it, and you keep just adding samples to this shared replay buffer. And then for each action you take in each environment, you update this shared network once. And so the fair comparison is that you have single task agent for all those tasks, and then you run them, and then you sum up the sample efficiency that you use for multitask learning and then for single task learning agents. And the problem, I guess, is that with multitask learning, even though some tasks are solved earlier, we still have to sample the transition from those tasks because of our algorithm, and we don't want to like do early stopping because it's sort of like a hack. So we want to make sure we train the agent. We do this until the agent to actually solve all the tasks. Then we say, okay, we multiply the number of samples it takes by the number of tasks that you are dealing with, which is this M total for multitask agent. And for single task agent, it's very simple. For each task, each agent, the number of samples you take, you just add them up. So some tasks can be solved earlier. And another thing to look at is, the point of multitask learning is that can we use some simpler tasks, samples from simpler tasks, to learn and then generalize that representation for the tasks that are harder. So we also look at the particular sample efficiency for particular task. And we first tried it on 9 tasks. So on 9 tasks, you could look at in the paper about which 9 tasks are. But with multitask agent, we were able to solve 9 tasks with 63,000 samples. And this means that you can you only used 7,000 samples for each of the tasks. And for single task, the summation was about twice of the multitask agent sample. I guess 1/2 of the sample efficiency for multitask. And we also added these 2 slightly harder tasks for our multitask learning. And we found that though it's not as good as the sample efficiency when done in 9 tasks, partially because those simpler tasks, you're still sampling from them even though you've solved them. So that's why it's slightly it's not as good as the 9 task one, but it still achieves better sample efficiency. And if we look at only the task particular sample efficiency, you can see the orange curve has a much better sample efficiency than the other ones because you learn those behaviors in the simple task. You're able to transfer them. So yeah, so I'll give a short video for this task, for the multitask learning. And it's probably hard to actually look at what's going on because there are so many, but yeah. So, okay. So yeah, so this was the search engine task we talked about earlier. And then that one is the social media task. And the other tasks are relatively simpler and then specific to particular action. Yeah. So are there any questions so far? Or?
Well, my first question is that can it transfer between different websites? For example, if you train it on Twitter logging and then it transfer to Facebook logging.
Right. So I guess so. This environment doesn't actually have. Sorry. So for this environment, I don't think it has that like diverse set of tasks. But if like I think within the discussion we'll talk about like how this could be scaled to real world websites. But yeah, in theory, yeah, if you have like if you can solve like the logging task in the Facebook, then you're definitely able to solve it in Twitter.
And my second question is that well, I feel like it's hard to imagine how this shared memory buffer works, because I was under the impression that the shared memory is a discrete key value store that if two states are slightly different, they will end up being in different places. For example, if you have a website that has a scroll bar that shows today's weather, then well, you take a snapshot, you take the state snapshot today and you show one weather, and tomorrow it shows another weather, they will end up in two different places in the well, in the memory buffer. So this, if this is true, then it seems like, you know, it's not really helpful in transfer knowledge. I was wondering if you know, my impression was wrong.
Can you repeat that again for the replay buffer part about?
So my question is that if the memory buffer
right.
in you used is discrete and does not rely on the similarities between two states. Because if it is discrete, then two very similar states, for example, one search page with a scroll bar displaying different weather information, will have zero relevance in the, well,
right.
the memory buffer, and which makes it not helpful in sharing knowledge in most of the case. I'm wondering if my understanding is wrong.
So you're basically saying if the states are very different, then there's no point, I guess, to do multitask learning, because sort of the network is trying to learn two different separate things with the.
But what if they're just slightly different?
What if they're just slightly different? I think over time, if you have enough samples, then it'll be able to like if they're actually, you need different behavior policy for those different states, then like you should be able to adapt to like different tasks. For example, here, some tasks are very like different. You might want to do some action in the email, or you might want to log in. There are some very different, but the point of multitask learning is like even looking at even learning about the representation, word embedding of particular text may be helpful for the other tasks. So maybe.
Can I just jump in? I think you can compare that to, for example, in image recognition, you feed an 8x8 image. Yes. You have two images. They're exactly the same, only here this pixel is black and here it's white. So this is what I think you're getting at, right? Where the inputs are similar, where the state representations are similar.
Yes.
Does it make sense to store them in the replay memory?
Well.
Or would it help?
It definitely does make sense. Well, but they will end up in different cells. And the reason that you know, the original learning paper used this is because, you know, the Atari game has very low resolution. So those two situations, two exact same image that has 1 pixel that are different, will both be covered extensively. In this case, they're definitely helpful.
Mm-hmm.
But, well, for example, if you have a portal page that has a scroll bar displaying weather, in which case every day's weather will be different. It will be a very big space.
You still have the DOM elements would be the same, right? So the only some individual elements within, like in fact, if the only difference is the weather, then out of all the DOM elements on your page, only a few text attributes, not even other attributes, only a few text attributes, maybe 2 or 3, would be different across these states.
And they will be outside the element.
They'll be inside the element because they're embedded in the. This is part of the state embeddings of the DOM model itself.
But so it's still very different from the Atari game situation. Because, sorry, could you repeat your statement?
I'm saying that
sure if I can
your example, if you have weather,
yeah,
on different dates, the states that represent these two dates would be very similar.
Yes, they are similar, but
let's take the rest of the
okay.
Is there any other questions? Sure. So when you took the argmax over those 3 Q functions, right?
Right.
If you could go back to that slide.
Oops.
Not that far.
This one or this one?
Yeah, this one.
Yeah.
So when you're taking the argmax, so my understanding of argmax is that you take the argmax over a probability distribution, right? So what is the probability distribution here, and how do you make sure that you are not missing any important sort of action or token or any component here? Because argmax gives you the one with the highest probability, right? But what if the one with the highest probability is not the right one? Right.
So obviously, Q-learning, it's a policy. I mean, value-based policy. It's a deterministic policy rather than like policy gradient. You actually model a distribution of your actions and you sample an action from it. Here, you basically you basically choose the action with the highest Q value, and it might not give you the highest reward, but that means your Q value. That means the Q value your neural network is like approximating is not good enough. So in your TD error, you have a high TD error, and you'll learn in such that you'll get better there. So, I guess should we go to the discussion? Yeah. Oops, sorry. Yeah, so I made some like sort of. Yeah.
I was wondering, sorry, I don't want to interrupt you because you have to straight, but I was wondering if you go back to that slide where you were talking about the shared weights in one case and non-shared weights in the other case.
Right.
Yeah. This one. Could you please clarify again what this was about?
So clarify this page.
Yeah.
Okay. Yeah. So actually I've kind of didn't mention, but here we have like 3 Q separate streams, and the first 2 actually use this type of Q network, while the third one, the mode, use this one. And the reason is that for the mode, you always know you either click or type, so your action space is fixed. So you're 2. So basically for the third one, your top has like two Q values. And then yeah, you can have something there, but that way, like, this is more efficient. Like, this is efficient in the sense that here what you're doing is actually feeding the action representation. And for DOM and token, the number of DOMs you're not sure. Like when you do argmax, you don't actually know how many actions are there for doing argmax. And same with token, because you don't know how many tokens you have. So for those ones, you actually have to use this shared weight, basically shared queue network. And then this will give you the queue value for that action and that state. And then this is less efficient because you have to do the same number of MLP here for each of the DOM in the graph. So is that okay? Yeah.
By the way, about, for example, the action of typing. So how did it come up with what word to type exactly?
So how does
clicking is like it finds an object and it does the click, but about the typing, I was like, can you clarify a little bit?
Right. Yeah. I guess for that goal, like this goal representation module, I didn't mention that much. But so for this Q token, what you basically need is you need this graph representation. So which is why we are feeding this global represent module to the token, because you don't need to know what like particular DOM, but let's say we're in a page, for example, for a search engine, we're in a page with the search box empty. Then this global module hopefully encaptures that sort of state, and then that's feeding the token. And then with that information, and we look at each value here. And now in this state, you need to actually type the word that goes in the search engine box.
You select the token, you find the token, and then you choose whether I should type it or I should, for example, click it. Is that the idea?
Right.
Oh, I see.
Right.
If I may be rude enough, because you already explained it, but there. So the part that you have two architecture, one with three output, 3 Q values, and one with only 1 Q value. The one that you just explained. One is more less cost efficient. No. The ones that you have those. Yeah, this one. So I still am trying to connect some of the dots here. So what's happening on the right? You take in state and action, and then you predict a Q value. And on the left, you see that you're taking a state, and then you output for three different Q values, given states and actions, right? I don't see how one is less efficient than the other. You did say something along the lines of more NLP work. So
so let's say we have like 3 actions. For this one, let's say that the computation within this, let's say the fully connected layer has only 3. Then you do a 4 pass, like for the MLP, you only do 4 pass one time, and then here you do like basically like you do a 9 multiplication because you have like 3 weights. But here, what you're doing is like for this part, for another action, you have to do the multiplication here again. Right. For each action, you have to do this. But the top part is this part of, I guess after this shared part, then the computation is the same. But it's mainly this intermediate.
So the input space is larger because you have S and A. Therefore, you.
That's not. That could be the reason, but the reason is like for getting 3 Q values within this network, you have to have this diagram, like two more of those diagrams.
Oh, I see.
So
okay.
Yeah, there.
Okay.
So the action space is not dynamic. Only the state space. State space is dynamic, right? For the action space.
So state space and action space is kind of vague here, as I mentioned, because your graph is your state space. It's also your action space. So the number of nodes in your graph is basically your number of actions. That number of actions you have to consider in that state.
Number of possible actions.
Yeah, number of possible actions. Yeah.
Can I actually ask you a question about this part here? I'm wondering, whenever you interact and do like one action, the graph itself, I would imagine that it would change some way. So say you entered a search, now you're dealing with a whole new
whole
graph.
Smaller or bigger. Yeah.
As you go through one problem, does that mean you have to retrain the graph embedding?
No. So because we're using sharing weights, right? So what you do in practice is like, in normal, like I guess, neural network, you have like two-dimensional matrix where the first dimension is your batch size, and then your feature size, right? So here, basically, so the batch size, like more like for sequential token, it's like number of tokens. And for each, you can basically, what you do is, for this kind of task, you flatten the third dimension. You flatten the third dimension such that it just looks like it's a two-dimensional matrix, and then you apply a neural network. You apply a single neural network to it, and then you reshape it back again into a graph format. I don't know if that explains well, but because we're using sharing weight, so it doesn't matter how many DOMs we have, our network architecture is still the same, because we're using this fixed network architecture for different DOM. So if you have more, you just apply this network to more actions, but your network is still fixed. So yeah, both networks are fixed. It's just this one can take in basically infinite number of actions, and yeah. So thank you. Yeah. So yeah, some discussion questions. Mainly, they're all about like how to actually use this in real world websites, because the problem with like current architecture or problem formulation is that those toy tasks have very small number of, they're actually not small compared to other tasks like Atari, because you still have like hundreds of actions. But in real website, the DOMs are like much bigger, and so how do we actually handle this sort of problem? And when I thought about this before, basically the simplest sort of way to deal with it is to add this intermediate action. Basically, let's say we have an action that let us focus on some part of the page. So remember, we had the mode. We can add an additional mode of focusing. So by doing that, we add an action such that our state space and action space at that state can be smaller. But then we increase the number of actions we need to take to complete the task. So there is a trade-off there. But obviously, there are some ways to deal with it. And from an engineering perspective, obviously, we will probably need some tools that filter out those noisy, trivial DOMs and give us almost very simple number of DOMs in that toy task. And that's the part for the real world website. Another thing is I thought about right now this environment, people program the reward basically. But how do we actually do it without this sort of programmed reward? And the simplest sort of work we could actually it's interested is that we apply some sort of a curiosity-based exploration. Basically, it basically says that if you can't predict the next state well, then you want to go to that state. So it's basically a count-based. There's a equivalence within the information gain and count-based exploration. But the idea is, yeah, we want to visit all the. Let's say we want to visit all the states in your web. Then what does the agent learn? The agent might actually learn the language such that it could actually visit all those states, or it might actually learn to hack some user because they're curious to see those states by breaking into this a login page or something. So it's another interesting, I guess, way to train it. Yes.
So out of those 23 actions that you tested, right, or you tried in this project, was there any drag and drop included in those actions,
Oh right, no.
No drag and drop.
So yeah, so in a social media task, for example, it actually has a scroll bar, but in my case, it gave me the entire very big DOM, the entire page. So yeah, it seems like it's not actually doing anything, but it's actually clicking something that you can't see out there. Yeah. So yeah.
So I guess one way to filter out trivial DOMs, I think, I'm not sure if you have explored this, but say using a simple image classification or segmentation or
to extract features from the image of the web page, and then you can say ignore ads or ignore useless widgets in a sense.
Right, I see. Yeah, so we could train. I guess we could train like separate like machine learning classifiers that helps us this process and make the problem easier for us to solve it. I see. Yeah.
Sorry, but how do you define trivial in that context?
Right. That's really task dependent. So which is very hard, and then it's like to make it to work on real website, we do like definitely need some experts who know like their websites and like what people usually write and what are the things that are trivial, and yeah. But yeah, feel free to come up with any discussion questions if you have.
I was a little curious about this multitasking. It was a little vague. Can you a little clarify it?
Right. So like the way we train it?
Yeah, what was the purpose of multitasking versus
right, so the purpose of multitasking is like we don't want to train an agent that can only do one thing. Then we have to train this big neural network for very simple tasks, and then we have to train for each. But if this agent can learn doing multiple tasks at once, then like we will have a better model. Like we just need to port this only one model and solve different tasks.
So by different tasks, you mean that the agent's exposed to a website, but it has to figure out what it should do with the website, right? Is that the idea? What is the task in here?
Right. So like the task, for example, like you want to learn how to do how to deal with the email sort of task, and then at the same time, given a different instruction, you might also want to do logging.
Like a person who is surfing the internet, that's exposed to different tasks on the internet. That's
yeah. So basically, yeah.
He's Internet Explorer, the agent, essentially.
Could you elaborate how, I know you said it, but well, it was also vague for me. So how did you, what was different from the part where I know that you're training on multiple tasks, but architecturally, what was different here?
Right, architecturally, it's exactly the same.
Then, I mean, perhaps I can go and look at the algorithm, but if you could facilitate that, or so questions that arise are, so then you're training. Do you have one data set of a non-homogeneous sort of data, or you train on one data set, move to the other? How is the objective function if it's different at all? Yeah,
so it's almost like you have like parallel actors, different parallel actors with the same network, but they have different objectives. By having different objectives, I mean like you basically have like 10 different environments, and you have 10 agents that act with it. But it's in a synchronous way, such that like at each action you have exactly the same network across different tasks.
Okay, so the objective function might differ, and the environments differ, but the architecture is the same. So basically, the weights are the same.
The weights are the same. Yeah.
To the best of your knowledge, is there anything that any papers or approaches that visually interact with web pages? So would use image classification techniques to try and find elements and interact with them that way?
So like the first work that proposed the architecture, they actually take in the image rather than this symbolic HTML representation. And it didn't work at all, because here the main component is actually to understand the text in the image. And with image classifier, they can classify like different animals, but it actually doesn't understand like the text, and like your token, you have a token, how do you extract that like word and then match it with your
You need OCR too.
Yeah.
It'd be hard to define your actions too, I think, from just an image.
Right, yeah. You basically have to, in that work, the action space is sort of like your pixel value in your image, so it's actually much bigger, because each pixel can be action there. Right. But yeah, it's
trying to picture if you could somehow map the HTML embedding to visual representations and then get more information that way.
I think that's really a good idea, that you can use like two representations, have some consistency, and then you may be able to like train agent that like learns, like transfers behaviors with different inputs.
Every everybody might use different CSS or different styling, right? And then you cannot just say that HTML representation or that HTML tag represents, for instance, this kind of picture, or even these kind of set of pictures or group of pictures for that tag, right? Because everybody's using different style, and that might create some problems.
That's
How many people actually customize their CSS realistically? I mean, like, most people take the stock CSS that comes from the site.
Oh, believe me, there are some people that they enjoy customizing almost everything.
Yes, but these people are not actually part of interpreting the page. Like, these people are outliers, and what they're doing actually doesn't tell us anything at all about how the page is meant to be interpreted. And actually going with the default CSS that ships with it tells us more about the intent of the person who created it. So I mean, I think actually, like, if you render it and rasterize it with a browser that's known to actually be able to do it faithfully, like in accordance with the designer's intent, that actually is a useful data point. Granted, all the information you get from that is also present in the markup, but the way that it featurizes it has potentially pretty useful. Now, if you're concerned about those edge cases, you could probably rasterize it with two different engines. Do one with Firefox, one with Chrome. Figure that 95% of the time it's going to be identical, and then occasionally when it's not, having two data points is useful, because an extra raster representation isn't that much extra data to throw in the feature.
So if I understand your proposal correctly, you're trying to use the sketch to call as some kind of adversarial oracle.
Kind of, right?
Yeah.
Is there a question? The question online, slide 25.
Okay.
Can you pick up my please? So can you repeat the question after I ask it? Slide 25. Can you explain a bit on the buffer? What does it do?
Okay, so the question is about this slide about the replay buffer. What does it do? So in off-policy learning, Q-learning, you basically want to reuse your transitions. By transition, I mean your state and then state action, next state, and then the reward. So the earlier TDA learning, basically you want to use that objective to train the network. So you can store this transition in the replay buffer, and then you sample a batch of them from the replay buffer, and then you keep training. So that's like the normal DQN replay buffer. But if let's say if you want to do a multitask learning, and you have like one shared replay buffer, meaning your agent acts in different environments, but those environments, I guess, still have the same problem formulation. So you can store this transition pair for each different environment, and then you can just sample some from this and then train it. So within like each batch that you sample from this shared replay buffer, it contains the transitions from different tasks.
Okay. Another question. Also, is there a way to track the learning rate of the agent?
So the question is if there is a way to track the learning rate of the agent. So by learning rate, I guess like it means like the reward that it's getting, like the recent like 100, like the previous 100, the moving average of your reward you're getting, which is a measure of how your agent is doing in most like literature. And for example here, this one basically shows like out of the last 100 episodes, how much reward are you getting? And by episode, I mean like the number of sequence that you take to complete a task. If you are able to successfully complete it, then it's 1. If you can't, then it's 0. And this basically shows like when you converge to this 1, you're always able to solve it.